Thank you very much, and thank you, Shirley and Julia, for the main work of the organization, which was indeed a lot of work. I've seen that. What I'm going to indeed try to do is to tell you the questions, at least from my point of view. I'm very interested in this field, which results out of the work of many collaborators that I'll be speaking about. But the main question is really the Graal from a mathematical point of view, is to understand the notion of regularity in very high dimension. How come we can indeed approximate these function of a very large number of variables with a relatively limited amount of data? So these functions in standard image processing setting would be, for example, classification. Given an X which has 1 million variables, which are the pixel of the image, find the class of X. But in a physical setting, the same kind of question will be X being the state of a system, for example, position charges of atom in a quantum chemistry problem, and f of X would be the energy. How come we can indeed approximate such function with models of low dimension? What is the underlying regularity of these functions which allows to do that? So that kind of questions, of course, extends to probability and statistical physics. In that case, f of X is the probability density, if it exists, of the random process. Can we describe random process as complex as turbulence? That's at the heart, of course, of statistical physics. And the kind of question which now appears is, can we describe a random processes whose realization will be phases, which are absolutely not ergodic? What does that mean? Can we indeed generate, approximate such random processes? So question, what allows us to approximate such functions? So the reason why we can ask that question, of course, is also because of deep neural networks. Because in the recent years, we've seen these computational structure able to approximate absolutely remarkably such high-dimensional problem in very complex and different settings. So these deep networks are essentially cascade of convolution linear operators with nonlinearities, which here are ReLU. And what we've observed is that they were able to solve relatively well problems such as image classification, sounds, language, regression problem in physics, all type of signals, but also generate images. So in some sense, build models of stochastic processes. But of course, the questions that we are all facing is the fact that these very complex systems are not interpretable. So we don't understand really what's happening inside. So what I'm going to try to do through the talk is to create simpler networks. And by trying to understand again that question, what is the underlying regularity which is being captured by these networks? How do they capture it? And as you'll see, there is really three ingredients that I'd like to discuss. First, multiscale. Multiscale clearly appears in the networks if you go deeper and deeper in the network, because the network do convolutions over a small neighborhood and iterates over that. When you go to deeper layer, you really aggregate information of a progressively larger support. So you see these multiscale phenomena happening in the networks. You also have, obviously, in physics, the notion of symmetry, which we see appearing here through invariance, because in these deep networks, when you go to deeper layer, you see that you are getting more and more invariant coefficients, and the answers of the network coefficient seems to be sparse. But I'm not going to go from an empirical point of view. I'd like to look at these questions from the first principles. So why multiscale? It's all over, obviously, in physics, and it's a very strong procedure to reduce dimensionality. If you take a problem with d-interacting bodies, in physics, particles, it can be pixels or people in the social networks. Usually, you have very strong interactions between a particle and its close neighbors. However, instead of looking at the interaction of all particles with the red one, what you can do is reduce the number of terms by grouping them. And the more far you go, you can build bigger group, and instead of looking at the interaction of each of them, you look at the interaction of the whole group, which creates an equivalent field, and you've reduced the number of terms from d to log d. And that's, for example, the principle of multiple techniques to reduce computations. Now, what is very difficult in this problem is that these groups also interact. And the whole issue is to understand how to build these interaction terms. So, separating scale, there are tools to do so. Wavelet transform, I'll be briefly speaking about it. What is really difficult is to capture scale interaction. This is a critical problem since the 1970s in harmonic analysis, and I think that's one of the elements that these deep networks are able to solve. So, the overview of the talk is I'm first going to look at these multi-scale separations and this issue of interactions, and we'll see appearing this notion of regularity across scales. And then we'll see how this notion, by using this property of invariance, can apply to things such as problem in statistical physics for turbulence, but also for quantum chemistry. Now, what we'll see is that deep networks do much more. And one of the questions is obviously, what are they learning? And I'll try to show that one element of it is sparsity, learning sparse dictionaries. And we'll look at, again, applications for image processing, but also generation of non-ergodic processes. So that's the topic that I'd like to look at. So the first question is multiscale. Obviously, it's all over there. How do you build a multiscale representation? Wavelets. So a wavelet is a local sine wave. This is a local cosine and the sine component. And what you do is you take your wavelet, you dilate it with different scales. This is the dilation factor. And in 2D, you rotate it with an angle theta. Okay, so you have this whole family of functions that you are going to use as filter. So you take your signal and you make a convolution with the wavelets. So if you look in the Fourier domain, the convolution is a product. What you really do is the product of the Fourier transform of your signal with the Fourier transform of the wavelet, which is located in some local region in the Fourier domain. Now, when you rotate the wavelet, you are going to rotate the support. So you are going to have different wavelets covering different frequency channels. When you dilate it, the support in frequency is dilated, and here are the frequency channels. Now, what's the problem? The problem is that when you have information in two different frequency channels, they are not correlated. If you look at the correlation of the wavelet coefficient along one scale and the other one, just by applying the Parseval formula, because their support don't cover, the correlation is 0. So basically, we fail to capture correlation across scales. So this is a wavelet transform. First finest scale, next scale, next scale. You see it cascade of filter like a deep net. All these images are non-correlated, but obviously they are very dependent. So the whole question is how to capture this regularity, this dependence. Okay, if you go to a problem such as modeling turbulence in statistical physics, what do you know? Stationary process. So your probability distribution is invariant to translation. What's the standard approach in statistical physics? You are going to try to build a model by specifying a limited family of models and defining a probability distribution which has a maximum entropy conditioned to these models, which has, therefore, a Gibbs form. Now, the natural moments you may want to impose are, for example, second-order moments. That means you impose that you know the correlation of your function with its translate. And in this case, as we all know, the probability distribution will therefore be a Gaussian. And that's the kind of models that you get. Now, what you see is you've totally lost the geometry. The problem is that Gaussian models don't use any correlations across frequency. Phases are completely random. And the whole issue, of course, in statistical physics is how to capture non-Gaussianity and long-range interaction. So a lot has been done by trying to use high-order moments, but it essentially doesn't work because you have too many moments, and these moments have a very high variance. On the other hand, deep nets gives you great images. So the question is, can we make sense of these very nice synthesized images? Now, a key element of the deep net is the nonlinearity, rectifier. Take a wavelet with a phase alpha. Take the wavelet coefficient and make a rectification. What's happening when you do that? If you take a Fourier transform relatively to the phase variable, you immediately realize that really what the ReLU is doing is creating harmonics of the phase. In other words, the phase is exponentiated. The modulus is not touched, but the phase is exponentiated. So if you take wavelet coefficient, this is the modulus, this is the phase. Here are their Fourier support. They don't correlate. If you take a harmonic, what is going to happen? You accelerate the phase. Now, if you accelerate the phase at that scale, now the phase moves at the same speed. In other words, the Fourier now are overlapping, and therefore, they can be linearly correlated. So you can build the same models, but instead of correlating the wavelet coefficient, you correlate the wavelet coefficient with the harmonics of the phase, which the ReLU gives you. So you have a limited number of moments, log d squared, less than second-order moments, and you build a model. You can sample your models, and there you get these DeepNet-like images where the phase coherence is restored, and you are getting things which are much closer to what is known to be turbulence, and that's being done in collaboration with Erwan Alice, who will be speaking also. Questions: how much physics are these models capturing? Essentially, we don't build high-order moments but of the modulus, but just of the phase. And what about non-ergodic processes? Questions I'll try to address a bit. Okay, so first point, ReLU are obviously very important. They allow to capture regularity across scale. What about other type of problems? In physics, n-body problems. Can you regress n-body problems, for example, in quantum chemistry? So a lot of work has been done. I think Gabor Siani will be speaking about that. He's one of these pioneers of this domain. X, in this case, is the state of the system. So it's given by the position of each atom and the charges of each atom. And what you'd like to compute is the energy. What do you know about the properties of the energy? You have information about the symmetries now of the energy. You know that if you rotate, translate the molecule, the energy doesn't change. It's invariant to these rigid movements. But you also know that it has a multiscale structure. You have very strong bounds between close atoms, but also very large interaction through van der Waals forces. So one of the ways to compute the energy with the DFT Kohn and Sham approach is to compute the electronic density. You see that the electrons aggregate close to the center of the atoms, but obviously are also present in between, and these are the chemical bounds. Now, what can you do from a point of view of regression? If you just go and apply the kind of approach that I've described, where you begin from your X, which gives you the position of the atoms and their charges, and you just convolve with wavelets and apply the ReLU. It's going to create all kinds of interference patterns that you see here. And then you build your invariants. How do you build an invariant? You just average over the orbit of the group, you average over translation, rotation, you get a whole family of descriptors which are invariant. This is a deep net, but there is no learning here, okay? You use your prior to specify scale separation and to specify the invariant. And then, if you want to estimate the energy, you do a final linear regression from a database. And that's just only supervised learning that you are doing here. What does it do on such a problem? So there has been a lot of database now put in together, like QM9, 130 organic molecules, which are essentially carbon, hydrogen, nitrates, and so on. These energies are computed with DFT, okay? And the goal is to try to regress these energies. Now, if you use such a structure, and there has been very nice deep net applied to that with a lot of learning, if you apply such a structure on a problem, the errors that you get on your regression is of the order of 0.5 kilocalorie per mole, which is of the same order that you get with a deep net where everything is learned. In other words, in that case, you don't need really to learn because you have enough from your prior. Now, to give you an idea, the error of DFT relatively to the true energy of a molecule is of the order of 2 kilocalorie per mole. So these regressions are very good. But these are very small molecules, 29 atoms, only 9 heavy atoms. And the reason why it works is very likely due to the fact that the problem is too simple. And that's what I would like to show now. When you apply that kind of techniques, so you just rely on multiscale and the building of invariants, for example, by translation, and that was the word of Johan Brunat for his thesis, and then you do linear regression. You get wonderful results on problems such as classifying digits. Simple problems. DeepNet do about the same, 0.5%. You really don't need to learn because you know in advance the sources of variability, translations, deformation. Textures, it works very nicely. If you go to a real difficult problem, ImageNet is a total failure. If you take ImageNet, which is 1,000 class, 1 million images for training, and here you can see, by analogy to physics, you have very macroscopic structures, much more complicated problem. The error, if you do that, is 60%. DeepNet, if you learn, the error goes to 15% in 2012. Now it's about 5%. So the question is, what is learned? And in fact, at the time, 2012, I did a bet with Yann Lequin, saying at the time I was very obnoxious, look, your DeepNet, everything will be useless. I'm sure someone will find a standard transform with a simple linear regression which will do the same. And we did a bet, and we bet a 3-star Michelin restaurant. Now, what is totally unfair is that not only he got the Turing prize, but I lost my bet, and I had to invite him to a 3-star Michelin restaurant in Paris. So the fact is, something is learned, which is non-trivial here. And the question is, what is learned by these networks? Okay, one hypothesis is that in some sense it's learning patterns. So what are patterns from a mathematical point of view? Think of a data X. You can represent this data X in a dictionary of patterns, which are really vectors that you store as the column of your dictionary. And the fact that X can be represented as few patterns can be expressed as the fact that it can be written as a product with a vector Z, which will have very few non-zero terms corresponding to the selected patterns. So the way this is set up in math is as a sparse L1 expansion. You try to approximate your data from a dictionary which is very redundant of vectors. You try to find the most sparse vector that will give an approximation, and sparsity is enforced by this L1 norm. Now, what's the relation with DeepNet? Let's look at how do you minimize this convex norm. So there has been a lot of research on that. In particular, there is this iterative soft thresholding algorithm. Now, the way you can minimize that is with an algorithm where essentially, iteratively, you are going to make a kind of gradient descent on the square term here, which will give you a first term, and you are going to incorporate the L1 norm through a soft thresholding with a threshold that you can adapt. So soft thresholding, you can write it also as a ReLU, is basically going to put you to 0 whenever you are smaller than alpha. Now, as let's say, nowadays, you cannot present an algorithm that way. You have to present it as a network. So let me show that algorithm as a network. You apply your matrix, you apply your nonlinearity soft thresholding, your matrix, and then you call that skip connection, and then you do the same thing, and that's the network which is implementing this algorithm which converge, okay, over K layer. But it's interesting to write it that way. Why? Let's put it, okay, so let me come back to the problem. If you apply on ImageNet directly your multiscale and imposing invariants, you get an error of 60%. If you take X, you try to learn a sparse dictionary. You do a linear regression, the error is still very bad. Why? Because X has too much variability. You cannot find sparse patterns. If you first get your invariants, and then you put a dictionary, and now this dictionary, which is this network with this matrix D, you optimize it in order to minimize the error. Okay, so you have a gradient descent. There is only one matrix, okay, in this network, which is unknown, which is D. The error goes about to 25%. So there is a huge jump. 25% was the result last week. So hopefully by NIPS in a week, we'll get 15% if we want to publish. But that's the idea. So somewhere sparsity plays a major role here. And sparsity, you need to learn it because you need to learn the dictionary. Now, if you can do that kind of things, then you have a network which is interpretable because the dictionary gives you, in some sense, the patterns within that space of multiscale which captures your information. So I'd like just to finish to show that that kind of principle can allow you to go from ergodic to non-ergodic processes, and that's the idea of these autoencoders. So as you know, in autoencoders, you take an image, you have a first encoder which transforms this image in something which looks like Gaussian white noise, and then you put a Gaussian white noise images, and then you try to invert this encoder with a decoder so that x tilde is as close to x. And then how do you do synthesis? You put an arbitrary white noise. So this is a network trained on bedroom. You get a bedroom. Another white noise, a bedroom. You can also interpolate between these white noise, and you synthesize things that looks like bedrooms. Okay? So it's very impressive. You can do that over faces. And if you interpolate, you put intermediate noise, you get other faces. It's as if you had synthesized a random process. Your input is white noise, and everything is in the decoder. Let me show that the same kind of ideas, which is capturing the regularity through multiscale and through dictionary, may give a way to understand these things. Let's do the same thing. You take your X, you build your multiscale representation, and then you build invariance by reducing dimensionality or local invariance. And you want to whiten out, so you're going to make a linear operator which decorrelates completely all the coefficients that you have here, okay? This is the white noise. So what did you do? You took your multiscale representation. This is an invertible representation. And then you applied a linear operator L, which has lowered the dimensionality and built a white noise. This is not an invertible representation. Why? Because you went to much lower dimension with L. And in fact, L is a mixing operator. That's what is going to Gaussianize your phenomena. So what should the generator do? It has to invert that. But this is an ill-posed linear inverse problem because you want to invert this operator L. Okay, how do you regularize such an ill-posed problem? You take what you want to recover. Suppose that you have a sparse representation of it. Your data is a linear operator applied to L. So you know that your data should also be sparse, not in the dictionary D, but over the dictionary LD. So you begin with W. You are going to build a sparse representation in the dictionary LD. L is known. Then you know Z. You apply your operator D to recover an estimation of U, and then you invert. Now, what you want is to learn the dictionary. How do you learn the dictionary which sparsifies UX? You don't know it. You try to make sure that the output X tilde is as close for all your realization to Xi. And you are just learning one matrix, the dictionary. So these are examples of training. That was the original random process, initially polygons. And after the dictionary training, that's on the training example, that's what you restore, something close. These were the faces, that's the faces restored by the decoder. Now, if you put white noise and you do a synthesis from that dictionary, this dictionary is now capturing the patterns of your problem. Over polygons, when you progressively change the noise, that's what you get, the intermediate polygons. Over faces, if you put, that's how, sorry, you see it here. These are random faces created from random noise in between two faces. It will be less. That's the last example, and that's what is potentially important for physics. One issue in physics is to build coarse-grained model. That's your model of turbulence, okay? But on a cell, what you measure is this, because you have a very coarse-grained model. And you want to generate randomly structures which looks like realizations of a phase, because this is a turbulent phase. What do? You put noise, and you put your random generator. All these phases are generated from this low frequency by putting random noise. And you see you have diversity. It may smile, it may not smile, and so on. Basically, you are building a model where this whole stochastic model is built over this sparse matrix over the multiscale representation. And it's essentially reproducing the kind of results that you have with autoencoders. And that's my 0, last slide. So what are the open problems? Everything are open problems around these things, essentially. Yes, what really appears, I think one of the remarkable elements that DeepNet brought is to go beyond standard linear harmonic analysis. Nonlinearity is very fundamental. Phase plays a very fundamental role. Physicists know about that, but harmonic analysts had forgotten that. And questions, is it enough, for example, to approximate complex processes such as turbulence? What's the relation with the Navier-Stokes equations? If it's indeed possible, we should see the evolution of these equations, these properties in Navier-Stokes. Okay, the proposition is multiscale sparse invariance. Is it enough or not? Are we capturing everything just with these three notions? Obviously, I'm not ready to do a bet with Yann Lequin right now, but still, I hope it is, but it's probably not. The fact that suddenly all your problems is parameterized by only one dictionary. Can we think about this approach for building interpretable model in physics? But these models are now resulting from the data, because it's the data which gives you essentially the different physical configuration. Last problem, I think, but I think Gabo will speak about that. The difficulty sometimes when we work on physical problem is that the problems are too simple, so we are getting amazingly good results. And I think that's a little bit what's been happening in quantum chemistry. And to move on, I think it's important to do the ImageNet type step that was done in image processing. Get really complex problem to see the limitation of the algorithms. And I'll stop here.
So first, just an asking question, I want to point out that there's a button on your seat and remind people to use that in asking it.
Okay.
Question, which is about intermittency. So one of the important properties of turbulence is intermittency. And so, you know, if I'm looking at a single realization, the statistics are varying. And turbulence, an important property is rare events. There are rare events where a lot of energy transport is happening in a small region at a given time. When you are computing these statistical properties and reproducing the appearance, you know, that's impressive. That's a nice step. But is the network able to reproduce intermittency? And in particular, what I wonder about this is one of the assumptions that seems to be going in when you're looking at different realizations is you're treating you're drawing from a Gaussian distribution that you then populate the wavelets and so on. But I wonder whether the distribution of amplitudes is one of these things that has a long tail to rare events. And one might need to do something like that to capture this intermittent behavior of turbulence, which is one of its important properties.
Okay, I'm going to try to give the element of answer that I know on that. On turbulence, whether here we capture rare events, I don't know, I would say probably not. However, what we did, the kind of test is on random processes we master, like multifractals, where we know everything about the high order moments, which are self-similars, like random Mandelbrot cascades and so on. And there, we do capture the high order moments with the phase correlation. But rare events, I think we won't capture it without a dictionary of rare events in some sense. And that's where I think dictionaries at one point are important. The reason is that the rare events won't appear in your statistics of your moments. And when you'll do your, that's why ergodicity is a very important property. And rare events in some sense are almost beyond ergodicity. And there, the hope is to be able to capture it with these dictionaries, but it's a question. I think it would be a very interesting test, in fact, if to have data where these rare events are well understood, and then try to see the failures of these algorithms.
So to follow up on that, can you actually turn, it's like about quantitative measure between your simulated turbulence and the real turbulence image? Can you develop quantitative metric? And also the other question, follow up David's question, suppose I want the real event to be reproduced. Can you use that metric somehow tune your network so that real events are produced? So you have this tailored simulation.
Okay, so about the problem of metric, the whole problem of turbulence is that because it's not well understood, we don't really understand what are the appropriate metric to really compare it with. And so, as I said, we didn't do it on the rare events. If one can characterize these rare events with other measurements with turbulence, it would be great to do it. It's very hard to verify that such a model is more or less appropriate on a random process you don't understand. And that's what's happening with turbulence. That's why we move to much simpler point processes, multifractals. But that's where I think physics can come in, because you do understand some of the physical properties, and one can try to see whether these or other models do satisfy them. I think the statistical problem is complicated because you don't understand the random process, so you don't know what are the statistical relevant measure beyond second-order moments. If you go to high-order moments, you have such a big variance on your moments that they are useless to verify.
But there's scaling relations between the moments in turbulence. You have a turbulence system in equilibrium between the 3-point function and the 4-point function. There are these scaling relations that would be interesting to see if you reproduce.
Yeah, that kind of thing, we have a tendency to get them because we are basically putting scale into the problem. That's what we verified in multifractals. That I'm less afraid than rare events.
Another question is going back to your image simulation. With your method, you get to 25%, right? But you only did a linear regression. Suppose after your transformation, fixed transformation, I do another simpler deep learning. How much would you get?
Okay, I don't know. We didn't try. These are recent. However, what I know is that if you get the invariance and you put a full CNN ResNet, you go back to the 5 or 10%. So you haven't lost information after the invariance, which shows that indeed the dictionary right now we are getting is not enough to go to, so some other things will maybe need to be done here.
I thought you maybe even right now can simplify a lot the deep learning structure. Right?
Yeah, the point is I don't want to go into the race. You need to go in the race of results again, otherwise nobody even listens to you. However, I find, I must say, nowadays with students, very hard because they have such a pressure to get results that you complexify the model and you can't do any math. So already with a single dictionary, the problem mathematically is in fact very hard because the learning of the dictionary, the property of the dictionary already. So I want to try to avoid before complexifying further, even if we get better results.
But I thought that could help you to see what's missing in the part.
Yes, I agree. That's, I agree.
Thanks.
Thiry.
I don't know if it's connected, but I mean, if you think about what Martin Heyer's been doing, he has been giving a systematic way to describe and talk about the nonlinearities in spatial processes, particularly vector-valued ones, and how you also, and I guess that'll happen here in some of these problems, how you have to do renormalization. Has anybody, I mean, it would seem to me intimately connected with the philosophy of what you're saying about how to look at the nonlinear functionals of the data. But has anybody actually tried to make the connection?
Okay, I don't know his work, but the relation with renormalization group, a lot of work has been done in the 80s. In fact, someone called Guy Battle wrote a whole book on the connection between wavelets and renormalization group, but that was in a linear setting, and it died a little bit. That's a very beautiful topic. We discussed about that with Giulio. At one point, that kind of thing needs to be done. To do the connect, I mean, Ising model, I didn't show you can reproduce Ising. Ising model is the nice, simple model where that kind of thing could be studied.
Yeah, but things like P542 or whatever, 543. I mean,
but
think about those without renormalization.
Yeah, we didn't do anything on that, but that's clearly a very interesting problem. Right.
So, can you also generate movies of turbulence, not just pictures?
So, well, not slide by slide. What you want is really to get the motion. To get the motion, you would need to model forces. For example, that's the kind of thing we're beginning to do in quantum chemistry. To generate movies, 3D simulation, the issue is to capture force, to regress forces. And the community has moved in that direction in quantum chemistry, which is regressing forces. We're going to try to do that. That's the kind of thing you would like to do in turbulence. Maybe, haven't done it, but yes. At least the question of approximating forces is the next question on the table in these problems. You don't want to stay with energy, and especially ground state energy. It's too simple in some sense. You want to regress forces, and maybe again, Gabor Siani will speak about it, but they are interesting.
Yeah. So I have another question, not on this actually. So the first question that you ask is, what is the regularity of the function that we can express or learn? So in the case, for example, of turbulence, but in general in statistical physics, in principle, you know everything about how these are generated because you know the microscopic equation. So is there some work on, let's say, abstract work that tells you what kind of regularity do you have for the, things that you are generating?
In Navier-Stokes, as you know, there has been a lot of work, and then there is $1 million hanging there for the one who finds the existence of solutions and stability. But particular, I know because there are many people in harmonic analysis. Yves Meyer, for example, used paraproduct with wavelets to try to get solution. But these techniques essentially were separating scales, and whenever you were trying to get the scale interaction terms, you were getting higher order moments, and they had a lot of problems to control them. Again, I think that question is very important. We will understand these kind of tools only if indeed we can make the relation with the equation, the microscopic scale equation. So we discussed about that with Keith Byrne to try to see whether one could do to make a relation between the two. I think it's needed. In fact, statistical physics is about that, building this link. And right now, there is no such link. But it's hard. I just want to stress on the fact that it's hard because there has been, 40 years of studies on PDE, even using scale separations and so on, leading nowhere. So there are new ideas coming out, from my point of view, out of these nets. But will it be enough? It's interesting to look at.
I don't want to stifle the discussion, but I think thanks, Stéphane.
Thanks.